Good morning, everyone. My name is Varushan. I'm based in the Joburg branch. And today, as my topic was stated, adversarial search meets reinforcement learning. So first, I'd like to start with what is adversarial search? To put it simply, adversarial search is just a method of searching where you're basically taking into account the actions of your opponent. You're always responding to your opponent and planning ahead. So just to lay the environments, first of all, our environment that I'm talking is deterministic, meaning if you're in an environment and you take an action, the resulting state or the fact that you made the action will always be 100% guaranteed. There's no probability of you not taking the action. The environment is also episodic. So if you take multiple steps in the environment and, for example, you're playing a game, you're talking about a game, the game will come to an end and then you can play another game. So each iteration basically just an episode or like one game. And then the last thing is that you have discrete actions, meaning you have a fixed amount of actions that you can take in an environment. So the next important step is decision making. So decision making is basically when you make use of certain types of algorithms to arrive at an optimal decision or an informed decision. So for today, in terms of adversarial search, we'll be going through two main algorithms which are mainly used, which will be the Minimax and Monte Carlo search algorithms. The Minimax algorithm simply, as shown in the diagram, where you have a game. In this case, if you take a game, you have the start state, which is at the top in white, and that represents the maximizing player. And in black, you have the minimizing player. The idea of Minimax is that my best move is the move that puts you in the worst possible situation, puts my opponent in the worst possible situation. So that's the idea. So the one player is maximizing their score, whilst the other is trying to minimize it. So when it comes to Minimax, the algorithm typically needs an evaluation function. So if we go back to the previous slide, you'll see at the leaf level or at the bottommost level, you need a way of attaching a value to how promising is this position. In this graph, for example, each edge is basically a move and each node is a state. So after you make a move, there's the resulting state and so on until you get to the leaf nodes. At the leaf nodes, you then need to have some sort of metric. Okay, how good is this position for the current player? How bad is it? We're just going to step through a quick example of the Minimax tree search. So in this example, it's the maximizing player's turn, as it usually is at the beginning. And we now search down the tree. And so we make a move and we get the bottom node, which is now the minimizing player's turn. And we then trace that one move further down, and now it's the maximizing player's turn. We now stop our search as we've reached the maximum depth, and we evaluate the node that we're at. In this case, we see that the bottommost node gets a score of 1, according to our evaluation function. Now, that's, of course, for the maximizing player. And so if we look at the other move that's possible in this state, we see that it gets a value of -2. Now, the minimizing player's interest is to minimize their score or get the smaller score. Therefore, out of the two possible moves that they can make, they would want to take the move that has the lower score. Therefore, the minimizing player would now take the -2. From the maximizing player's perspective, they want a higher score, of course. And this means, well, in this case, there's only one possible move, so they have no choice but to accept -2. Now, the maximizing player will then explore another move if that's possible. And the same situation happens where we now reach a leaf node that has a value of 1. We have a second leaf node with a value of 0. And the last leaf node has a value of 2. So from this, the minimizing player, of course, will choose the 0 because they want the lowest possible score. And now the maximizing player has to decide, okay, is this entire branch worth switching moves over for? And so that's what ends up happening. The maximizing player now, if they make the move on the right, is guaranteed a score of 0, as opposed to having -2, which means they were losing. The Monte Carlo tree search method is another type of search method. So if you looked in the Minimax method, we actually expanded the entire tree. So also in games that have a lot of possibilities, there's a lot of nodes to expand, and it's not feasible computationally. So the Monte Carlo tree search is actually an asymmetrical tree search algorithm. Therefore, it does not expand the entire tree. Rather, it will expand the nodes that look more promising. So I will now show you a quick demonstration of the Monte Carlo tree search. This is basically an interactive Monte Carlo search on tic-tac-toe. On the left here, I will make the first move. So if I, for example, here, and then ask it to make a Monte Carlo move. And the first procedure of the Monte Carlo search is selection. This is where we choose a node that is worth expanding. So if I go to the next action, at first we will select the root node, since that is the only node in the tree. And what we've done here is that we've expanded a state. And this state basically checks if the Monte Carlo agent goes to the bottom edge. Now, the next procedure is simulation, where from this state, we now play random moves on the board until the game ends, either in a win, loss, or draw. In this case, the winner is the Monte Carlo agent. And this is obviously good for the Monte Carlo agent. Now, what we do is now propagate this win up to the tree, all the way back to the root. So in the case of this, we have now get a value of 1, because it's +1, is the win. And the parent node now also gets a visited score of 1. Now this procedure is repeated. So now we select again. Selection simply descends down the tree. And we now have this metric, which you might have seen, called UCT. UCT is short for upper confidence for trees. And it's basically a measure or a metric that's used to measure out how promising each node is and whether or not we should explore it. So if I quickly go back to my slides, as you've seen, the UCT metric is basically balancing these two aspects. One is exploration, which is if we're searching for a move, how much do we care about exploring moves that we don't know will be good? So I think for most players, even for chess, you always try and you think about sacrifices. If I sacrifice this piece, will it actually benefit me in the long term? The other aspect is exploitation. And this is basically exploiting the knowledge you already know. So if I know that, example in chess, bringing out my bishop early in the game is good development, I'm exploiting the knowledge that I already know. I'm not searching for something that is. Now that I get to the UCT formula, this formula simply is, as I said, metric to measure which nodes should be explored. The first term on the left here will simply be that for the current node that I'm on, how many times have I won in this set, right? And then you're simply dividing by how many simulations so as to measure a win rate whenever I came to this. The second aspect remains to represent the exploration calculation. This simply converts and it works out how many times have I visited this node relative to its parent. So if I've not come to this node very often, then this fraction will be very, very small. And then that's why it's meant to become larger if you visited the node a few amount of times. The speed parameter is something that is dependent on the domain you're working with. And sometimes you want to prioritize exploration more than exploitation. So if I just continue this demo, so the same procedure repeats for, in this case, 1,000 time steps. And so if I just visualize the last step, you would see that the final tree that's generated is simply one where every possible move is explored. But if you look here at the bottom, you would see that only this one move has been visited 532 times of the 1,000 iterations. This goes back to Monte Carlo being an asymmetrical search algorithm. It did not visit every single branch evenly. It actually focused all of its computation on this specific move because it seemed promising. Actually, this is actually the optimal move. If Monte Carlo does not go, or if an agent does not go into the center, you can simply create a situation where you can force a win by having 3 of your in this case X, on the outer edges. So the main issues with adversarial search on its own is computation. As I said, with Minimax, you need to expand the entire tree, and even if you limit the depth, you're visiting every single node in the tree, even. That's a lot of computation. Evaluation. So in the case of Minimax, you need an evaluation function. If you as a developer are working on something and you do not have a way of evaluating, or your evaluation function is very bad, then your Minimax search is also going to give you bad news. The last aspect is improvement. And whenever you're working with an agent that is basically set in stone, the evaluation function is fixed, it's never going to improve. If you give it a single state and you ask for a move, it'll always give you the same thing. So now that I come to reinforcement learning. Reinforcement learning is simply a way of an agent learning from its environment. Now, from this diagram, you can see that the agent takes an action inside the environment, it gets a reward, and it gets the resulting state. Since the basic topic, we are now trying to join the adversarial search with the reinforcement. The logic will be more or less the same. All that's simply happening now is that you will now have things like a neural network trying to learn the evaluation function. And in the case of Monte Carlo, the UCT formula I showed you will now incorporate a value function and a policy function. So in the case of supervised learning, what will happen is that the agent will now look at multiple games played by professionals. So in the case of a board game, it will now look at multiple games having played by professionals and will tweak its value network and policy network to suggest moves that are similar to that in those board states. So the main issue with supervised learning, of course, is the fact that now you're injecting bias to the system. Since you're asking it to play like humans and play the moves that humans have played, you've now created this bias. That is one of the biggest issues with injecting information into an adversarial search algorithm with reinforcement. The other option is then unsupervised learning, where the agent simply starts off with no knowledge of the game, simply just gets the rules of the game. What happens is then the agent versus itself over and over again. And based on the outcome, for example, if I call the agent on the left agent A and the right one B, then if A won, then all of the states leading up to the win for agent A will now get a positive score, in the case, for example, plus one. And then all the positions of player B will get a negative one. And this is how you can basically tweak your evaluation function over and over again after playing multiple games. So the main issue with RL is that, in a way, neural networks is meant to represent how we think. And what can happen is that since everything is connected, there's always clouds of knowledge about the game that the agent might not understand. And this is where it will lead to delusions, where the agent might think it's winning, but it's completely losing, and it just doesn't realize it. This is something that can be ironed out with rigorous training and testing, but it's still not guaranteed that it's completely gone. And so with adversarial search, there have been many successes. So one of the main successes is AlphaGo. I'm not sure if you guys know, but this was the exact same algorithm that I explained, Monte Carlo search, where there's a policy that's being learned and a value that's being learned. And these things are used in conjunction with the Monte Carlo search. This was done in the game of Go, and it's basically one of the most computationally expensive games to create an agent for. But they were able to create an agent that would beat the best Go player in the world. So adversarial search really ties into the whole idea of, if you have a large state space and you need to make informed decisions, that's usually where you can tie in reinforcement learning. And like I said, just with these successes, it now shows that you can take so many domains, if any, that require long-term planning and decision-making. You can simply inject reinforcement learning, self-play, and Monte Carlo search. Get very, very desirable results.